So I would like to ask, is it Favor Mulungi? May you please unmute and lead us in an opening prayer. Favor Mulungi. Favor Mulungi. Please unmute. Favor Mulungi. If not Favor Mulungi, then let me ask Bridget Jones to unmute and lead us in an opening prayer.
Okay, let's humble ourselves and we pray. Almighty God, we thank you for this day. We thank you for the gift of life. As we're going to have this lesson, may you guide us, protect us, enable us to understand whatever we're going to learn. And above all, may your will be done. In Jesus' name I've prayed. Amen.
Okay, thank you so much for that. Let me start by introducing myself. Let me do the introduction when my video is on. My name is Sevu Ronald. I am a teacher of physics and mathematics right away from St. Paul and Pauline's. That is the school where I teach. It is in Masaka, St. Paul and Pauline's Masaka. So I welcome everyone who is on the call right now. I thank you for the time which you have put in to make sure that you connect, you join us in this meeting, because we cannot flow well when you, the participants, the learners, are not on. I would also thank everyone, every parent who has allowed their children to be on this call today. So we are going to be generally in physics. That is, the topic is going to be sound waves. We are going to be dealing with sound waves. And that is a topic which is, according to the syllabus, it is learned in the second term of Senior 3. But we decided to do it during this time because there may be some people who have not yet covered it. Then there may be those people who have covered it, but they didn't get it well. And also there may be those people who covered it, but they did not cover it fully. So we want to expound more about sound waves. And in this lesson, we are going to be using both audio explanation and video clips. So we shall be using video clips to help us expound more about the concepts in sound waves. And also, as we are here, I would like everyone who is on the call to be with their pens, to be with their pencils, to be with their calculators, because we are going to be doing activities involving calculations. So we shall be carrying out calculations, and I would like every member to be participating in every calculation which we are going to be tackling. So I encourage you, if you don't have a pen there, if you don't have a piece of paper and a calculator, please, you may just use a minute to get them, or to get them, and then we start there. Yeah, that is it. So allow me to share the content of today's session. That is the outline of the session, the areas where we are going to be discussing. So it is going to be about sound waves. Then we shall talk about how sound is produced as a form of energy, then the properties of sound waves, then the transmission of sound through solids, liquids, and gases, Then demonstrating the fact that sound requires a material medium for its propagation. Then determination of the speed of sound in air using echo method. Then we shall also talk about reverberation of sound and how it is minimized. So all of these, I pray that we deal with them in this scheduled time, that is from this time to 4. Then I think we shall cover them. We shall not spend a lot of time on them because the concepts will be clearly explained in a few minutes by the video clips and the audio explanation. Anyway, the audio explanation is by me, but we shall not take long. I expect to finish these within the stipulated time. So that is it. So as we are doing this, first do this. Okay, so everyone who is there, how sound is produced as a form of energy. Now, since we are in sound waves, we are going to be dealing with sound waves. I expect everyone to be with some knowledge about the general properties of waves. If not that, how can, anyway, the nature of waves, the production of a wave. So someone to know that a wave is a disturbance in any medium, you should be knowing that because we are going to be dealing with waves. So going into sound waves without you knowing what a wave is going to be quite difficult, but it's fine even if you did not cover it. It's fine. So, but we need that knowledge. So we are going to be talking about the knowledge of waves. So even if you did not cover it, we are going to be talking about it, but less we shall be dealing with more of sound waves, but the knowledge we are using here is going to be of waves. Now, sound as a form of energy. Everyone, if you don't have any hearing impairment, or if you are not impaired in listening, there is no one here who has never used the sound as a form of energy. Because right now, it is what we are using for you to listen to me. Now, how is that sound produced as a form of energy? It is what we are going to start with. That is our first bullet we are going to deal with. How is sound produced as a form of energy? It is what we are going to deal with for right now. So allow me to do something from this background. Oh, and even if I don't, anyway, even if I don't make this side, even if I don't hit my table, you can hear me. My voice is received from the microphone of your computer or from the microphone of your phone into your ears by sound energy. So the sound from the microphone of your phone, from the microphone of your, it is not the speaker. It is the speaker of your phone, from the speaker of your computer. It comes to your ears by the sound energy. So which form of energy is this and how is it produced? So everyone from there, may you please raise your hand and help me to, may you please raise your hand to help me answer this. How sound is produced as a form of energy? If you have some hint about it, because Sound energy is not new to us, but how is it produced? If you can raise your hands. Yes, I can see here, Jesse. Jesse, may you please unmute and respond to that? How is sound produced as a form of energy? Jesse? Hello, Jesse. Someone there to raise their hand to respond to that, how sound is produced as a form of energy, because you may be knowing it. May you please share with us how sound is produced, because I don't want to just go into it. I want you to be knowing something, and then we go into the video clip, and then we expound more about it. Yes, those ones who are raising hand, let it be from the reactions, not from the chat. Yes, Erin, this is Erin. Erin from the chat box has said that sound is produced through vibration of particles. Thank you so much, Erin. Then Karen is saying sound is produced as a form of energy through vibration of objects. By hitting an object, someone has said that is Akia, then through vibrations. Thank you so much. We shall go with those, but also allow me to share this video clip to you such that we can get to know where it is 3 to 4 minutes of how sound is, what does it mean by vibration, and what are the vibrations they are talking about as the way sound energy is produced. So please allow me to share this to you such that we can expound more about what are these kinds of vibrations which bring about sound energy. So please, this is.
There is so much noise here. This noise is caused by different sounds that we can hear with our ears. Hey Bubbles, do you notice that some sounds are louder than others? I wonder what sound is. Yes, and I wonder how it is produced. We are surrounded by different sounds all the time. Some sounds are pleasant, such as music, the chirping of birds, and the water flowing in a river. Some sounds are unpleasant, such as the sound of traffic. Sound is a form of energy. Let's see how this energy is produced. Look closely at the surface of the drum when it is beaten. What do you observe? The surface of the drum is moving up and down. Now, place some small pieces of paper on the drum and beat it again. What do you see now? Oh, the pieces of paper are jumping. The quick up and down or back and forth movement is known as a vibration. Sound is produced due to the vibration of matter. We can define sound as a form of energy that is produced when particles of matter vibrate. To understand vibrations, let's perform another activity. Put Put your fingers to your throat and say something loudly. What do you feel?
My throat is vibrating.
You're right. We produce sound through the vibration of the voice box in our throat. Similarly, when a metallic spoon falls, a sound is produced. The impact of the fall causes the spoon to vibrate. We can also observe the vibrations of a speaker when a song is played. Time for an exercise. Can you identify the source of sound when a guitar is played? To play a guitar, the strings of the guitar are plucked. This causes the strings to vibrate and produce sound. Time to summarize what we have learned today. Vibrations are the quick back and forth movement of the particles of matter. Sound is a form of energy. Sound is produced due to the vibration of the particles of matter.
Okay. So that has been our clip to the introduction of sound energy and how sound is produced. Let me hope the video has been clear to everyone. Has it been clear to everyone? You can just inform me in the chat box. Because if it is not clear, then I make the way it can be clear. Aha, that's so good. Thank you so much. So that's how sound is produced. That as long as matter is vibrated, then sound energy will be created. There will be sound energy. So even when you just talking, the voice from your mouth is not just a miracle. The voice is not just a miracle, but it is after the vibration of your throat, then the vibrating throat creates that sound energy. Anyway, from the vibration of the throat, then the vibrating particles, that is formation of sound energy. So please, from there, there is a summary which is made that the sound energy, the way they summarized it is that the vibrations are the quick back and forth movement of particles of matter. So whenever matter moves, whenever the particles of matter vibrate, do up and down movement, then that is a vibration and there will be sound energy. Then sound is a form of energy. It is not just a miracle, but it is energy, like as we know the other forms of energy, like heat energy, like light energy. Also, sound is a form of energy. Then also, sound is produced due to the vibration of particles of matter. As long as the particles of matter vibrate, regardless of the states of matter, because even the particles of a gas, when they vibrate, there is sound production. Because you can just make a disturbance within air, then you will hear sound that you have disturbed the air molecules and they vibrate. After vibrating, then you hear that sound. Then also, even if you put something in calm water, for example, when you have some water in, let's say, a bath, let's say a basin, then you drop some small stone there. There is a disturbance within water. If you were able to put your ears in water, you will be able to hear the sound. Then for you will, who is not in water. The sound you hear is through air, but not through water. Then also, a solid also, when the solid is disturbed, if the molecules of this, if the particles of a solid vibrate, then there, a sound energy will be produced. Now, take an example. If you want to feel that vibration of solid particles, if you are on a table, let's give this simple activity. You just put your ear on your table. Let me just try to put my ear on the table as you can see me. But I don't know whether you will be seeing me. You just put the ear on your table and you bang at the table like that. So for me, I hear the sound of the knob I have made on my table. Then for you can also do it from there and see that even in solid, this sound can travel there as long as it is matter, because the sound, it requires a material medium for its propagation, because sound cannot travel somewhere where there is no matter. But as long as there is matter and that matter is disturbed, there is a vibration in that matter, then sound energy will be produced. Then we can go back to our share. That, let me hope you have noted something from there, that sound energy is produced due to vibration of particles of matter. May you produce, please note that. Sound energy is the form of energy which is produced due to vibration of particles of matter. Then the vibrations are quick back and forth movement of particles of matter. Yes. Please be noting, because as we are going, we shall be needing this knowledge. You need to remain with this knowledge. So not somewhere, don't just listen. Anyway, listening and grasping the things in the mind, it is the very good thing. But if you forget somewhere and there is a concept which you have forgotten, it is quite better if you could go and recall from where you wrote your notes. Then also, let's go to the next thing. We have seen how sound is produced. Also, we have seen how sound is produced. Then from there, after the production of sound, we are going to something else, which is properties of sound waves. Because you have seen that sound is a wave energy. Sound energy, all energy, forms of energy are waves. So sound, the vibration which is caused within a medium, produces a wave. So that wave causes, from the knowledge of waves, that when a disturbance disturbs matter, then the vibration causes transfer of energy from one point to another. Then we have seen that also sound energy is due to the vibrating particles. So these vibrating particles result into what a sound wave is. And that sound wave is sound energy. So we have to know the properties of these sound waves. What are the really properties of the sound waves? So the properties of sound waves, we are going to look at few of them, but I will urge you to go and make a research about the more properties of sound waves. So we are going to look at the wave nature of sound waves, the wave nature, that which type of waves is sound waves. How do sound waves move from one point to another? Then, if it is a wave, then which kind of wave is that? Then, to those people who have some simple knowledge about that, properties of sound waves, I would like to ask something. What are they? May you please mention some properties of sound waves? Or as we are mentioning, let us first talk about the kind of waves sound waves are, because we have two kinds of sound of waves. We have the mechanical waves, we have the electromagnetic waves, those two, the mechanical and the electromagnetic. Then also, taking those two aside, the mechanical and the electromagnetic, then there is also transverse and longitudinal waves. Then we are going to start by identifying which kind of wave is sound waves in terms of electromagnetic and mechanical. Then from there, we also talk about the transverse and longitudinal waves. Which kind of waves does sound wave fall in those two groups of two, because they are mechanical waves and there is also electromagnetic waves. Then taking those aside, then there is also transverse waves and longitudinal waves. Then where does sound waves fall in those four? It has to be falling in two of them. So which kind of waves is sound waves? That's the properties of sound waves. Knowing those, the two types where sound waves fall, then it will be easy for us to know the other properties of sound waves. Because if you cannot tell where it falls, then the other properties will be disturbing you. You will be getting a difficulty in that, because you have to be knowing that, is sound electromagnetic or mechanical? Is sound transverse or longitudinal? Then other properties will be gotten from those two major ones. Then I would like to come to the participants about the properties of sound waves. Let us start with mechanical and electromagnetic. Which of the two does sound energy fall or sound waves fall? Which of the two? The mechanical and electromagnetic. Which of the two? Let me just check from the chat box. From the chat. From the chat. Sound waves are type of mechanical waves. That is Macklin. That is from Macklin. Then someone is saying period, speed. Your hand is up, sir. Let me just check from the people who have raised their hand. But let me first check from the chat box. Sound waves are electromagnetic and longitudinal. That is Erin to everyone. Then sound waves, that is longitudinal. Hannah Musime, thank you so much. Sound waves follow under longitudinal waves. Thank you, Zanita. Then properties of sound waves. Someone is saying amplitude, wavelength, frequency. Those are general properties of waves. So we just want sound in particular. Then it is mechanical wave. That's mechanical waves. Thank you so much for your responses from the chat box. People, you are really active. I appreciate you for that. Let me just check from these people who have raised their hands. There is Katrina Sela. Katrina Sela, may you please unmute and respond. Which kind does sound waves fall? Is it electromagnetic or mechanical? Is it transverse or longitudinal? Yes, Katrina.
Sound waves.
Yes.
They are mechanical.
They are mechanical.
Yes. And they are longitudinal.
And they are longitudinal. Thank you so much, Katrina. Let me also listen from Caleb Erickson. May you please unmute? Caleb Erickson. Caleb, do you hear from us? Okay, let us go with those responses. Let us go with it. Yes, Caleb.
They are mechanical waves because they require a medium for their transmission.
Thank you so much for that response. They are mechanical waves because they require a material medium for their transmission. It has been a bright response. Thank you so much. You have put a reason as to why sound waves are considered to be mechanical. Thank you so much. Yes, others, thank you, but Caleb has brought it the way it has to be, that sound waves are mechanical because they require a material medium for their propagation. If you don't have gas, if you don't have solid, if you don't have liquids, you cannot transmit sound. If where you are, there is no matter, sound cannot be there. Sound energy cannot be transferred. So take that note that if where you are right now, from the place where you are, if there was no air between the speaker of your phone, between the speaker of your laptop and your ears, if there were no air, then you could not hear my voice from your speaker, because sound requires a material medium from the speaker of your PC to the ears. Then also, I myself to speak, the sound energy to move from my mouth, the voice of the sound of the voice into the microphone of the speaker, it needs a material medium, it needs air. So if air was not there, you could not hear me, because sound could not move from my mouth to the speaker of the computer. But since there is air between my mouth and the microphone of the computer, and there is air between the speaker of your computer and your ears, there is transfer of sound energy, of transfer of sound waves. So the vibration is, there is a disturbance in the air. Then in that air, the energy is transmitted through that air as the medium of propagation. So if you are underwater and speak something, if that water was not there, sound could not be heard. But if it is there, then sound can even be heard when people are underwater, because water is a material medium which can transmit sound. So sound waves are mechanical waves because they need a material medium for their propagation. So from that property of being mechanical waves, then we can say that sound waves, from mechanical waves, we can break like 4 properties, if not 3. We can look at requiring a material medium for their propagation. So that one being mechanical, it requires a material medium for their propagation. If you cannot say like that, then someone can say someone can say that sound cannot travel through a vacuum. Nico Williams, I see your hand is up. May you please say something? Nico Williams, Jr.
Teacher, I wanted to say that sound waves are longitudinal waves because they have an amplitude and they also have a pitch. So that's what makes them.
They have an amplitude and they also have a pitch. From sound waves, is it really clear when we say longitudinal wave, from the knowledge of waves, that we talk about amplitude? Nico Williams, about longitudinal waves, may you expound more about amplitude?
Okay.
Of longitudinal waves.
Okay, amplitude is the Amplitude is the distance, like okay, the distance of a sound wave.
Of a sound wave.
So yeah.
Now this one will be more. Okay, you can mute. This one can be more explained when we go to the difference between longitudinal and transverse waves. With the longitudinal waves, you may not get it clear with amplitude but with the transverse waves, you will get the amplitude because there is that vertical vibration of particles. So that one will be more clear with transverse waves, but with longitudinal waves, it may not be clear because the vibrating particles, we are going to see how the vibrating particles in longitudinal waves vibrate. You will notice that the amplitude will not be clear as you have spoken it. The amplitude will not be clear to you. But when you talk about transverse, the amplitude will be more clear because in the transverse waves, the vibrations are perpendicular to the direction of vibration, and that perpendicular distance will be there, that distance from the mean position in the amplitude. So with the longitudinal waves, it's not fine to talk issues of amplitude. Yes, Macklin, your hand is up. Do you have something?
Yes.
Yes.
Is the maximum displacement of a wave particle from the position.
From the mean position. Yes, thank you so much, Macklin. Now, the amplitude with the longitudinal waves does not apply. It applies to transverse waves. You are going to see how the vertical displacement come with transverse waves, but not longitudinal waves. So that is it. So with transverse waves, with longitudinal waves we are going to see how sound is categorized as a longitudinal wave. And please allow me to share something because there is some confusion is about longitudinal and transverse. So we are going to first start with the transverse waves. You see how particles vibrate, and that from the definition of transverse waves, that there is the particles vibrate perpendicular to the direction of propagation of a wave. So you are going to see that direction and what brings amplitude. Then after there, we are also going to see our main part, that is how sound wave is transmitted. That is how the longitudinal waves, because sound wave is a longitudinal wave. So as you are making your conclusion is there, please conclude like this. Sound wave is a longitudinal wave, and also it is a mechanical wave. So from the properties of longitudinal waves, you will get other properties. From properties of mechanical waves, you will get other properties of sound waves. So properties of longitudinal waves also apply to properties of sound waves. Properties of mechanical waves also apply to sound waves. That is it. So that one helps us to expound more about the properties of sound waves. Yes. So this saying is the sound cannot travel through a vacuum. Sound requires a material medium for its propagation. All of those ones can really be explained by those two. If you look about the general wave properties, and then you go to properties of mechanical and the properties of longitudinal, then you will be on the properties of sound waves. Then please allow me to share something about, let me first see, we are going to share something about the transverse waves, how the particles vibrate in the transverse waves. Then also with that, we shall also expound more about, let me see, longitudinal transverse wave, yes, it is here. It is here, let me just share it. So within this share content, the share video, it is going to expound more about how vibration is, how do particles vibrate in a transverse wave. Then we shall go also, they are directed to longitudinal waves, and you get that difference, that clarity in their meaning, the perpendicular vibrations and the parallel vibrations to the direction of propagation of a wave. So please let me share something here and then see it. So this one is going to show us the particles in a transverse wave, their vibration, how do they vibrate, and their vibrating direction. Please note the vibrating direction and the direction of a wave. Those two, they bring the meaning of a transverse wave. Please listen and note something.
Why do you not look? Hold the other end. How does the ribbon move? Which direction the wave move? The disturbance travels from free end and to the fixed end.
So you can see, I'm opposing. You can see that this one, this arrow, shows the yellow arrow, shows the direction. This yellow arrow, this one, shows the direction of the vibrating particles. And this ribbon, which is tied on our rope, this one is just representing that one particle. In this medium, the medium of propagation of this wave is this rope which we have tied this one. So, someone can just unmute, can mute. So we are saying that this ribbon which is tied here represents the single particle in this rope. How does that particle vibrate? You can see that for it, it vibrates up and down in one position. It does not move. But these red arrows, they show the direction of vibration of, they show the direction of a wave. They show the direction of energy. The wave moves in this direction, but the particles vibrate within this position, only one position, but the energy moves in that direction. So as you can see that, let me just remove these annotations and you bring the clarity of the direction. So you can see the direction of vibration is upwards. The direction of the vibration is upwards. And let me just draw it like this. Is upwards, vertically upwards. Then the direction of movement of a wave is horizontal. So there is that angle, the right angle between the direction of movement of a wave and the direction of vibration of this particle. So in a transverse wave, the particles are perpendicular. The vibrating particles are perpendicular to the direction of flow of a wave. So that those are transverse waves, and this is not sound waves. So you can see that the up and the move up and down vibration bring amplitude in transverse wave. So you can see that. So as you are there, please get the difference or get the real meaning of a transverse wave and how it is meant to be transverse. The direction of vibration, the direction of vibrating particles is perpendicular to the direction of a wave. So please allow me to continue and you get it more according to the explanations of the of the video. Let me just take it back like this. Okay.
Tie one end of the rope, wind the ribbon on rope. Hold the other end of the rope and move it up and down. How does the ribbon move? In which direction does the wave move? The disturbance travels from free end and to the fixed end. When waves are formed on the rope, all that happens is just the ribbon moving up and down, whereas the ribbon's position on the rope does not change at all. The ribbon is vibrating in a direction perpendicular to the direction of propagation of wave. That is, each particle of the rope vibrates in a direction perpendicular to the direction of propagation of the wave. Such waves are known as transverse waves. A transverse wave is a wave in which the particles of the medium vibrate in a direction perpendicular to the direction of propagation of the wave. Tie one end of a rope to a wing.
Okay. That is about transverse waves. Now, you are going to also allow me to share something about longitudinal waves. So you have seen how particles vibrate in transverse waves and how energy is transmitted through a medium without the movement of the particles of a medium. Remember the definition and the meaning of a wave. This ribbon represented a particle. For it, it vibrates from that position, and the energy moves within the medium, but this particle does not move from that position, from that point. You can just see it just simply. The energy moves from those waves move, you see them move. But the particle, this rope does not move as the direction of it, but for it to just vibrates within one position. So you can just see. So you can see the particle just moves, the ribbon is in one position, but the waves move. You can just see. Let me hope that has been clear. It has even brought it more clear in the definition of a wave. The transfer of energy through a medium without the movement of a medium, or without movement of medium particles, without the movement of its particles. Let me just check something from there. Then also, we can just go back. We can just go back. Someone has also talked about the mechanical properties of waves: diffraction, interference, reflection, transmission. Yes, that is fine. Every wave will undergo those properties. Please don't forget that all waves can undergo diffraction, interference, reflection, transmission. That one is fine. Also refraction. All waves can, even sound can be refracted. Take note of that. And also, in refraction of sound energy, you can just take it as a research work. How is the sound refracted? Then you will expound more about that. Then let us go to the form of energy which sound waves is. That is longitudinal waves. Let me stop this share and I bring how the longitudinal waves, how do they vibrate? Let me just do it. Longitudinal is here.
Fix one end.
So with the longitudinal wave, I would like you to note this as I'm going to share it. I would like you to note this, that their compressions and rarefactions, not troughs and crests. So I would like you to note the compressions, the rarefactions. We are going to use a spring Remember, a spring can produce longitudinal waves. It can also produce transverse waves, but in this case, we are going to see how a longitudinal wave is formed by a spring. That is it. So let us look at it, and then we continue. So there we go.
Fix one end of a slinky to a wall. Hang some pieces of papers.
So as we are going through this, I would like you to note these 2 points. The point, let me just annotate here. Point A and point B. I would like you to note the way energy is moved from point A, from this point where the hand is, to point B. As you are looking at that video, please, as you are watching it, take note of the 2 main parts of a longitudinal wave. Those are rarefactions and compressions. So please take note of them and see how they are formed. Because even you, from your home, you can do this. It is very simple. So I want you to see that this particular point A is going to be vibrating, but in one position. For it does not move, but the energy moves along this medium. The medium is the spring where the energy moves. So these waves which are going to be watched in this video are longitudinal. It is going to be a longitudinal wave. So please, let us watch it. There we go. Let us go back.
Fix one end of a slinky to a wall. Hang some pieces of papers on the coils at equal distances. Press a few coils on the free end A, held in the hand, and then release them. Now a region of high pressure shift from A to B. But paper pieces do not move from A to B.
So from there, I would like to make it clear to those ones who have not identified it, the 2 major parts of a longitudinal wave. There is this point of low pressure, this one. And there is this point of high pressure, this one. These 2, this one and this, they are this is energy moving from point A to point B. This is what they call a longitudinal wave. This is a this is a compression where there is too much pressure, the point of too much pressure. Then this one, point of low pressure, is a rarefaction. So please note them. As you go back to the general properties of waves, these 2, you talked about them. So that's how a longitudinal wave is. So let's just continue with this video, and then you shall see other things. Okay. There we go.
Here the energy is transmitted from A to B.
Let us go back about that energy.
Move from A to B. Here the energy is transmitted from A to B without translatory motion of particles. Here the coils are vibrating as in the direction of wave motion.
So, let me just go back a bit and bring.
But paper pieces do not move from A to B.
That's where I wanted you to see, to get the difference between transverse and longitudinal waves. With longitudinal waves, you can see that this particle, the way it vibrates, this A, the way it vibrates in the direction, in this direction. You have seen it moving like this and then coming back, moving it like this, and then coming back. That is the vibration it makes. For it, it makes vibrations which are parallel to the direction of a wave. These red arrows, they show the direction of a wave, the direction of energy through this medium. So, as it is moving, moves from this point to this point, the direction, the energy moves from point A to point B. And then this particle A at A, for it, it vibrates. It does not move. For it, it vibrates. But the way it vibrates, remember, vibration is to and fro movement of a particle. So it vibrates like this, like this, like this, like that. So for it, its direction is the direction of vibration is parallel to the direction of a wave energy. That is it. So please, let us continue, and you realize that the direction of this particle A is parallel to the direction of a what? Of a wave. So thank you, as we are finishing this, to go to something else.
Here the energy is transmitted of particles. Here the coils are vibrating as in the direction of wave motion.
Okay, that has been the difference between longitudinal and transverse waves. So sound wave is a longitudinal wave as it is being the sound energy as it propagates within a medium, it propagates like the way you have seen it in that spring. It is longitudinal. For it, it does not do this like it is not like water waves, these common waves. No, for it, it makes rarefactions and compressions. It's vibrating particles vibrate vibrate parallel to the direction of a wave. As the wave is moving through the medium, then the particles vibrate in the direction which is parallel to the direction of a wave. Not like in water waves. For water waves are transverse, then sound waves are longitudinal. So longitudinal waves, let me hope you have seen it. So in other ways, we are going to see how does sound travel in different media. You will see that as it travels in a form of longitudinal waves. It travels by compressions and rarefactions, but not crests and troughs. It moves with rarefactions and compressions. So as we go to our outline of the session, let us see the next thing on agenda as we go. Yeah. So from there, we have seen properties of sound waves. Mechanical, the properties that sound waves are mechanical, that is one of them, one of the general properties. The major, let us say major. Sound energy is a mechanical wave. Sound waves are mechanical waves. Then sound waves are longitudinal waves. Then the properties of mechanical waves go to properties of sound waves. If a mechanical wave requires a material medium for transmission, then it means that also sound waves require material medium for their transmission. If mechanical waves, to make that point clear, if mechanical waves cannot be transmitted through a vacuum, that is a vacuum where there is no matter. So it means that also sound waves cannot travel through a vacuum. That is it. So the properties of longitudinal waves, if you get the properties of longitudinal waves from the general properties of waves, then they also come to properties of sound waves. Then the sound waves, the properties of longitudinal are the properties of sound waves, because a sound wave is a longitudinal wave. That is it. So from properties, let me hope I've been quite clear. Let me just look from the chart. From the chart. Let me hope from the classes where you school from your schools. Let me hope they are. I don't expect a teacher who was very happy about people who discuss in class, but they don't. But what they discuss is out of the content which is covered in class. So those people who are in the chat box, may you please, let me say, don't shout for us. If you are discussing in the chat, you discuss according to the sharing content. You give your views. The people who are there, it is fine to discuss within the shared content, but not something out of the content, because this is an online class, but you are making online noise from the chat. So please, don't just chat. Don't just chat. That is it. Don't just chat. Don't just chat. Let me hope I've been clear to that. Don't just chat. Okay. Let us go to the transmission of sound through solids, liquids, and gases. So the transmission of sound through liquids, solids, and gases is going to enable us. The transmission of solids, of sound through solids, liquids, and gases is going to enable us compare how sound travels through these three media. Okay? Through these three media. So how does sound travel through solids, liquids, and gases? And how do they differ? How does the speed of sound differ when it is in solids, liquids, and gases? So when is sound faster? Is it faster in solids? Is it faster in liquids? Is it faster in gases? Then what causes it? What causes the speed of sound to be fast in a given media? And what causes the speed of sound to be slow in a given media? So allow me to share something about the transmission of sound through solids, liquids, and gases, and how they are compared. Then I want you to note something. We are going to respond about the comparison between the propagation of sound in these three media. Okay? Then what causes them? Yes, it is faster in a gas. It is faster in that medium which you have mentioned. But do you know the reason? Please, let me share this to you, and then you be more clear about it. Thank you so much. Let me do sharing. Let me do that sharing here. It's here. Video sound. Okay.
Speed of sound.
Okay. So there we are. I would like you to pay more attention about these two videos because they bring it more clear to why sound is faster in a given medium than the other. So please be attentive as we go through it. Okay.
The speed of sound is different in different media. Sound travels with different speeds in different media like solid, liquid, and gases. Sound travels in a medium due to transfer of energy from one particle to another particle of the medium. Since the particles of the solid are very close to each other, so the transfer of energy from one particle to another particle takes place in less time. Hence, speed of sound in solids is very high. In the case of liquids,
so let me hope that you have captured that. Let me just go back a bit.
From one particle to another particle takes place in less time. To another particle of the medium. Since the particles of the solid are very close to each other, so the transfer of energy from one particle to another particle takes place in less time. Hence, speed of sound in solids is very high.
So you have taken that note that since the particles in solids are close to each other, the transfer of energy from one particle to another is very fast, because sound energy requires those particles to be transferring, to transfer energy from one particle to another. So since the particles are closer in the solids, the rate at which the energy is transferred in the solids, the rate at which it is transferred is faster, because the particles are near each other. From one particle, it does not require a lot of time to transfer the energy, the vibration from one particle to another. Since they are close, so please take note of those, that in solids, particles are closer to one another, and then it requires little time for the energy to be transferred from one particle to another, as we are going to be making our conclusions.
Hence, speed of sound in liquids is less than the speed in solids. In case of gases, the particles are far away from each other as compared in case of solids and liquids. Hence, the transfer of energy from one particle to another particle of a gas is quite slow. Therefore, the speed of sound in gases is less than the speed of sound in solids and liquids.
So, have you noted something about that? That the speed of sound in gases is less than the speed of sound in liquid, and also less than the speed of sound in solid. Have you noted the difference? What brings that difference? The speed of sound in solid is higher than the speed of sound in liquid, and also than the speed of sound in gas. So please, from the chat box, let me first check from the chat box whether you have gotten it more clear with a reason, with a reason from the three media, solid, liquid, and gas, where does sound travel faster? That is our question. Where does sound travel faster? In the three media, solid, liquid, and gas. Please put that reason such that the members can check whether you have gotten it well or not. So we are checking. It is faster in gases? No. You have not been attentive. You have not been attentive, members. Hey. So please take good note of the information in the videos, because from the chat box, people are no longer chatting, cannot send some message. Maybe it is different with every teacher, the way they teach. You get right. Anyway, not different with every teacher, but it is, physics is a science. You can always, I would like to always encourage you to make research. I would like to always encourage you to make research, not to be depending on just our teacher told this. Because you can even correct your teachers. Don't you correct your teachers? You correct your teachers. You have to be correcting them. Hey, whenever they may do something and it is not for all time, you never know they had mistakenly done that thing. So please look at, which condition did they bring? Because in some conditions, there are other conditions which have to make things different. Don't just take it like that. Don't just take it like that. Sound travels faster in solids. Thank you so much. Sound travels faster in solids since the particles are closer attached to each other. Thank you, Will Snipe. Thank you, but the names. Okay. Sound travels faster in solids. Thank you so much. Then there is someone here who has said, Tim, it is solid because they have the closest particles, hence faster transmission of energy. Thank you so much, Tim. Then Maya in Enrinka, I will go with your names which are displayed here. Solid is because it is very high and faster, but also takes less time. There is some, it is not quite not clear, but you will get it well. That is it. Then there is also something about the elasticity of a medium. Did you get to know about that factor that affects the speed of sound in these three media? The elasticity of a medium. Please, the video which we are going to deal with brings it more clear. I would like you to be attentive about this, about elasticity. But before going to the part of elasticity of the media as a factor which affects the speed of sound in these three media, let me just ask some people to raise their hands such that they can respond by voice. Esther N, may you please unmute and respond to that. Twice, in which media does sound travel faster? Yes, tell us how you have gotten it.
Sir.
Esther N. Yes,
Sir.
please.
I wanted to ask first of all.
Yes.
Okay, it travels through solids faster, but I was asking, can you please pardon me on the transmission of sound through the solids and gases?
The transmission of solids through, but the transmission of sound through solids and gases. Solids, liquids, and gases. It is where we are right now. It is where we are right now. The transmission in these three compares, it is about their particle nature and how faster it is. Because remember, the transmission of sound is about vibrating particles transferring energy from one particle to another. That is the general transmission of sound energy. That is the general transmission of sound energy. Then, in solid, liquid, and gas, since they are particles which transmit energy, the sound energy, then the transmission we are talking about is how faster is sound in a solid, liquid, and gas. That is where we are. Yes, it requires a material medium. That material medium has to be with the particles. Those particles have to vibrate. As they vibrate, energy is transmitted from one particle to another. Then, how does that transmission of energy from one particle to another differ in solids, liquid, and gas? The difference in transmission of energy comes with the speed at which that energy is transmitted. That is the point where we are talking about that. We are on transmission of sound energy. But the difference in the transmission of sound energy comes about with how faster is that energy transmitted from one point to another within that given medium. If it is a gas, how faster is sound transmitted from one particle to another within a gas? If it is a liquid, how faster is sound transmitted from one particle to another within a liquid? If it is a solid, how faster is sound energy transmitted from one particle to another within the solid? So that is where we are. It is where we get the difference from. You get? So as we go back to this, because it is just 1 minute, I would like you to pay attention about it, that the transmission of sound in these three media. Let's move.
The speed of sound. Sound travels with the speeds of media, solid, liquid, and gases. Sound travels in a medium due to transfer of energy from one particle to another particle of medium. Since the particles of the solid are very close to each other, so the transfer of energy from one particle to another particle takes place in less time. Hence, speed of sound in solids is very high. In the case of liquids, the distance between the particles is large compared to the distance of the particles in solids. Thus, the transfer of energy among different particles is lower than in solids.
So you can get that in liquids, the distance between the particles is quite larger than the distance between the particles of solids. That's why in liquids, the sound energy is slower than in solids, because it takes some longer time to transfer energy from one particle to another in a liquid than it is in a solid. Please.
And the speed of sound is less than in case of gases, particles are far away from each other as compared to the case of solids and liquids.
So you can hear from the video that in gases, the particles are far away from each other than in solids and liquids. So the distance between the particles in gas is longer than the distance between the particles in liquids, and also longer than the distance between the particles in solid. So you can hear that. So that difference brings the reason, as we are going to hear it from this video. Please be at it.
In case of solids and liquids. Hence, the transfer of energy from one particle to another particle of a gas is quite slow. Therefore, the speed of sound in gases is less than the speed of sound in solids and liquids.
Okay. That is it. So that brings transmission of sound in these three media in line with the particles, the particle arrangement, the distance between the particles. But let me hear from someone here who has raised their hand. That is Kiza Apollo. May you please unmute and say something? Kiza Apollo.
Yeah. Yeah, it is faster in solids.
Yes.
And the reason is the particles in the solids are closely packed to each other. So the vibrations are transferred faster. So making it being faster in the solid state.
If there is JK, may you please unmute and say something? JK, are you online? Okay, let's hear from Nana. Yes, Nana. Nana, may you please unmute and say something? Okay. Let's look. Jelly Cats, are you there? Please unmute. Jelly Cats.
So, sir, to me, it's faster in solids and liquids because of the high elasticity. When I talk about the elasticity, this is whereby these two medias, it is because of they can rapidly return to their original shape after compression and expansion.
Yes. Okay, thank you so much for that, Jerry. Yes. Also, in solids, there is the reason as to why sound is faster in solids than in liquids, then next to gases. It is because of the higher elasticity of solids than liquids and gases. So as we are doing this, elasticity of these media also is also a reason as to why the sound travels at different speeds within these media. Then we are going to also look at it. So as we are looking at it, that video explains more about how the issue of elasticity brings that difference in the speed of sound and the difference in the transfer of energy. So please, let me stop this share. You take note of what we've shared here, that the speed of sound is faster in solids than in liquids and gases because of the difference in the distance between the particles which transfer energy. The particles in solids are closer to one another. So it takes little time for energy to be transferred from one particle to another. Then also, in liquids, the particles are quite far away from each other than in solids. So it takes some longer time to transfer energy from one particle to another in liquids than in solids. It takes longer. So it means that in liquids, it is slower than in solids. Then also in gases, the particles are far apart. The distance between the particles is far apart compared to the liquid and gas and the solid. So there it will take much time to transfer energy from one particle to another. So let us go to elasticity as a factor which affects the transmission of sound energy in these three media: the solid, the liquid, and gas. So please allow me to take some time as I share this. Okay. This one.
Hello, students.
Okay. So let me share this video to you. Please be attentive as we are going to that thing of elasticity. Let me hope everyone here has covered something about the mechanical properties of matter, because we shall need that knowledge to get to know more about elasticity. Please, there we go.
Hello, students. So from our previous modules, we all have understood that sound, it travels through the air by forming compressions and rarefactions. That is, it travels as a longitudinal wave and it needs air to propagate, as was established by the bell jar experiment.
Now the question arises, can sound travel through other medium as well? Well, to answer this question, let's carry out a simple activity. So students, just lay your head on your study table such that your ear touches the table. And now scratch the table gently with your nails. So do you hear any kind of sound? Well, yes, you will surely hear a distinct sound. And that's because the sound travels from the table to your ear. And you must know that the sound, it travels faster in solids than in liquids and slowest in gases. Now, can you give me a reason as to why the sound travels fastest in solid as compared to liquids and gases? Well, it is so because solids, they have much higher elasticity as compared to liquids and gases. So now, what do you mean by this term elasticity? Well, elasticity is defined as the property by the virtue of which a material, it is able to deform when a force is applied and is able to get back to its original shape or configuration when the force is removed. So you can see here, when I remove the force, it comes back to its original shape or configuration. Well, students, mark my words that anything that is easy to deform is not the only measure of elasticity. As for example, if we take the case of a steel wire and a rubber string, then what do you think? Which of these is more elastic? Well, you would be surprised to know that the steel wire, it is more elastic than this rubber string. And that's because if this rubber string is pulled, then we can say that it is merely more stretchable. But it is not very elastic, or I can say that it is less elastic. And what do we mean by this term less elastic? Well, in physics, we've defined elasticity as the resistance to change. So the greater the resistance to change, the greater is the elasticity of the material. And the faster it comes back to its original shape or configuration when the deforming force, it is removed. So this rubber, it is less elastic than this steel wire. So students never get confused with this term of elasticity and never think elasticity as something as something which is the amount of stretching, as both of them are completely different from each other. Well, students, let's return back to our topic where we have discussed that sound travels fastest in solids as compared to liquids and gases. And that's because solids, they have much higher elasticity as compared to liquids and gases. Thus, more the elasticity of a medium, faster will be the speed of sound in that particular medium. So students, now if you see the solid substance at the molecular level, then it is characterized by molecules with strong forces of attraction for each other. And these molecular forces of attraction, they can be considered to be as springs that control how quickly the particles, they return to their original positions. So the particles that return to their resting position quickly are ready to move again more quickly. Thus, they can vibrate at much higher speeds. Therefore, the sound can travel faster through the mediums with higher elastic properties like that of steel than it can through solids like rubber, which have lower elasticity. Now, another reason why sound travels fastest in solids is that in solids, the molecules, they're closely packed together and they're tightly bonded. So being so close to each other, they can collide very quickly. That is, it takes less time for a molecule of the solid to bump into its neighboring molecule, thus causing the disturbance to move forward in very less amount of time.
Okay, so that is how it has been explained about elasticity. The ability to regain the original shape, go back to the original shape. So the solids cannot be, the way they are stretched faster, the way they are stretched further is not as that compared to gases and liquids. The liquids have low elasticity because they cannot regain their original shape fast as in solids. So in solids, the particles can easily go back to their original shape when they are disturbed. Let's take that a little bit clear, that when you make a disturbance, that is a wave in the solid particles, that the solid particles, the solid being more elastic, it is that when the particles are disturbed, when the disturbance has gone, it can come back to the original position. Then it carries another disturbance. That energy and the elasticity of a solid, like the quick coming back to the original shape after disturbing the particles of a solid, enables it to transfer the energy faster. So that is how it comes to the factor of elasticity as the factor which makes the solids to transfer sound faster than other media, than gases and liquids. That is it. So as we are in this, I'm seeing some people are raising, but is Martha, do you have something? May you please unmute? Martha, I see your hand up, or we can just move. Yes, Martha.
I found out what I was looking.
Okay, thank you so much. Thank you so much for that. Then there is something I want to share with you here. From the beginning, we saw that sound is a mechanical wave. It implies that sound requires a material medium for its propagation. General properties of mechanical waves. That is the major one, that they require a material medium for their propagation. Now, have you ever done an experiment or a demonstration about that? Or you just hear it from the books? Or you just hear it from the Belgian experiment? You can, if you have those materials, you can easily do that. But please, I have some simple, it's a short video clip which can show us something about that property, that sound can only travel where there is matter, material medium, where there is matter. Remember, mechanical waves cannot travel where there is no gas, or where there is no liquid, or where there is no solid. Sound can only travel when there is one of those three media. It can travel either when there is solid, or when there is liquid, or when there is a gas. That is it. So I have some simple demonstration about that fact, about the Belgian experiment, to show that sound really travels through, can only travel where there is a material medium. It is not like electromagnetic waves. It is not like light. If you go into details, you see that light can even travel through where there is no matter. Where there is no matter, light can travel. Even heat energy, heat waves can travel where there is no matter. Even other electromagnetic waves. But for sound, you just need matter for it to propagate from one point to another. So allow me to share something about the Belgian experiment. It's here. Okay. There we are. Let's move. It is just 1 minute.
Take an electrical bell and an airtight bell jar. The bell is suspended inside the airtight bell jar. First, press the switch for the bell and you will be able to hear the bell clearly. The bell jar is connected to a vacuum pump as shown. Now, start to pump the air out of the jar gradually. You will hear the sound becoming fainter, although the same current is passing to the electric bell. Soon you will notice the less air is left inside the bell jar, the less the sound becomes. If the air is removed completely, you won't be able to hear any sound. From this experiment, we can understand that sound cannot travel through vacuum.
So that's what I wanted to show you about this bell jar experiment. Sound requires a material medium for its propagation. The theoretical, remember, there is a way we did not get it well when our teachers our teachers back in time did not show us these things. But this bell jar experiment is quite simple. If you observe it and see how it is done, you just get a bell jar, then then you put an electric bell in it. Then that electric bell has to be connected to the power source to power it such that it can operate. Then from there you switch.
First, press the switch for the bell, and you will be.
So when the switch for the bell is on, the bell will start ringing. So as it rings, then remember, for us, we want the fact that sound cannot travel where there is no matter. So inside that bell jar, there is air and the electric bell. But we want that space in the bell jar, which is covered by air, to be free of matter. So the space just around where there is no bell, where the electric bell is not, we want it to be free from matter. So the matter which is only there is not a liquid and a solid. It is only a gas. So there is gas inside this, there is air inside the bell jar. So we have to suck this air inside that bell jar using a vacuum pump. A vacuum pump sucks air. So as the vacuum pump sucks air, remember you had switched on the electric bell and it rings. Before sucking the air, you hear the sound. So as the air is sucked, the sound goes on fading until it completely wears out. But you will be seeing the bell jar being, the electric bell, the gong of the electric bell being hit by the hammer, which shows that the hammer is hit. The sound which would be produced by the hammer, by the bell inside the bell jar, does not travel into your ears, because inside the bell jar there is no material that can enable it to move into your ears. That is it. So you can see the bell being hit by the hammer, but no sound is heard. So you can just be attentive to this simple video and get that result.
To hear the bell clearly. The bell jar is connected to a vacuum pump as shown. Now, start to pump the air out of the jar gradually. You will hear the sound becoming fainter, although the same current is passing the electric bell. Soon you will notice the less air is left inside the bell jar, the less the sound becomes. If the air is removed completely, you won't be able to hear any sound. From this experiment, we can understand that sound cannot travel through vacuum.
So that is the conclusion from where we've been discussing, that Sound being a material, being a mechanical wave, it cannot travel where there is no matter. So it needs a material medium for its propagation. As we are moving, there is, I don't know whether you can hear it from my room, but I know from your schools you have many halls. Have you ever entered a main hall and which is empty, without desks, without chairs, without curtains? Have you ever entered there? I know you have ever, because there are always activities which at school, which require, maybe to some schools, which require you to take out the chairs, to take out the desks, to clean that main hall. So, have you ever made a loud sound inside that main hall? What do you notice? There is some repetition of the sounds of your voices. For example, if I, Ronald, is speaking inside a main hall, empty, there is no chairs, no desks, no curtains, nothing, but just empty. Then you make a sound. You can just hear your sound being repeated continuously as it fades. So that is an effect of sound. Now, what is that? Did you know that we use that sound to determine the speed of sound in air? Did you know that? That those repeated sounds, they are the ones which are used to determine the speed of sound in air. Because you make a loud sound, then it enables you to determine the speed of sound in air. The repeated sounds, from the knowledge which you have, general properties of waves, it is there. It is a property of waves. Which property is that? Let me just check from the chat box. Which property enables that repetition of voices when you are in a main hall? Which property? To those people who are in areas where there are highlands, like highland areas. Let me talk about people from, we have someone from Fort Portal, that side. Then also, not even Fort Portal only, but also in central, but where not in cities, because cities have buildings. But I want somewhere where you can just stand up a hill and then you make a loud sound. You can hear your voice being repeated as if it is going somewhere far, like someone is repeating your voice running away from you. We used to play with those voices when we were young. Remember, for us, we grew from villages. We grew up from villages, so we could just go to up the hilltops, and then we make those sounds. We could be happy of hearing those things like repeating themselves. So, which property brings that? Because before me studying physics, I didn't know that it was a wave property that brings about that repetition of my voices. So from the chat box, I can see someone is saying echoes, sound waves can be reflected. Thank you so much for that property. Sound waves can be reflected. Thank you so much. Someone is saying reflection of sound waves. Thank you so much for that. For real, you are good learners. It is a good class. Someone is saying, let me just check. Check. For real, you are a good class. The bouncing of sound, which involves the production of sound again, and it is called echoes. Thank you so much. Someone is saying reflection of sound waves. Thank you so much. The property is reflection of sound. Thank you. Resonance? No. Check. For those to that one who has mentioned the resonance, I would like you to give you a task to get to know the real meaning of reason is how the frequency of one sound be taken by the other. Not resonance, they are echoes, reflection. Thank you so much. That is it. So how do they, let me just check something from the hands, but our time is running up, but we are going to make sure that we cover something about reflection of sound. The property is reflection of waves. So sound being a wave, remember we said, all the properties of waves, the general properties of waves, sound has all those properties, can undergo them. So there we have seen an effect of the effect of this property, that waves undergo reflection. So also sound is a wave, it undergoes reflection. So how we move, how does that occur? How does sound come to reflection? Yeah, what is it? How is sound reflected? Is it that you can hear that sound from everywhere? How is it that you can hear that repeated sound from everywhere? What conditions enable you to hear that repeated sound? Then if we want to determine the speed of sound in the air using the reflected sound, how do you do that? So there is some simple video here which I would like to share with you about that effect. First of all, we are going to start with the effect of that reflected sound in an empty room. How does it differ from the echoes which are heard by someone who is, for example, up on a hill? So I would like to share something in 2 to 3 minutes before closing this. And as we are closing this, I would like you, please, since we have gotten some information about sound as a wave, we have not completed. We have not dealt about how to determine the speed of sound using echo method. It is where we've been heading, but let it be an assignment if we don't expound it well. Then also we have to talk about reverberation of sound. Reverberation of sound. That reverberation of sound is caused by echoes. So let me share to you something which we've been going to talk about before our time ends. So we are just left with these two. Determination of the speed of sound in air using echo method, then reverberation of sound and how it is minimized. Determination of the speed of sound in air using echo method, we were going to carry out an experiment, to look at an experiment and do some activities. But to those ones who can screenshot, please take this as an assignment. May you please screenshot these last two items. These last two items to be your research activity. These last two items, please. Then, as we are there with these last two items, the first item, determination of the speed of sound in the air using echo method, I'm going to share with you the session activities which I had prepared. I wanted you to do it within the session, but the time of the session is running, and we should not go beyond the stipulated time. We should not go far beyond the stipulated time. So I'm just going to share you the questions which I had prepared. Yes. So the session activities, before the session activities using echo method, we are going to see that video, but please help me and take a screenshot of these activities. Take a screenshot of that. Let us just use a few seconds. Let's count for 1, 2, 3, 4, 5. Let me hope that is taken. Then let me also scroll downwards to take these last 3. 1, let me just make this one clear. Okay, 1, 2, 3, 4, 5. Yeah, those 5 seconds are enough for you to screenshot them. Then it means that you are going to carry it out as an activity. From the research, from the videos which we are going to play as we are finishing, then you will be able to do that. Then take note that using the echo method, the speed of sound in the air is determined from this formula. The velocity of sound equals 2 times the distance, then divided by the time taken. We are going to see how come is that the distance is multiplied by 2. Then you will also research more about it. And as you go back to your discussion, if you have the naysayers who can be in a discussion with you, then you can expound it more by trying these 4 activity questions. Then you will be able to get it clear about the determination of speed of sound in the air using echo method. So let me stop this share. Then I share for you the video about echo method. And because we have some, not in 5 minutes, we shall be closing this session. Measuring speed of sound by echoes, so it's fine.
Measure the speed of sound using some. How do you measure the speed of sound using some wooden blocks and a wall? We take a measuring wheel to measure the distance between this man and the wall. Let's say that's
okay. So when you want to determine the speed of sound using the echo method, remember the property echo is the reflected sound. So this person who is standing there in front of a wall, this vertical wall can reflect sound. So when he makes a sound, that sound will propagate from him to this wall. And then this wall will bounce it back to him. Then what this man just wants, this person, he just wants is to determine the time it takes for that sound to travel from this point to this, and then coming back. Remember, the echo is the sound which you hear after meeting this barrier and then coming back. So you time yourself. You start the stopwatch at the instant you make that loud sound. Then you stop the watch when you hear the sound again. Then that time which is measured, then you also get the distance between you and the wall which has reflected that sound. So after getting that distance, remember from the formula, from distance equals speed times time. Then our speed of sound will be equaling to the distance traveled divided by the time. Now, the distance traveled by this is not just d. This is from here to here. If we call it d, from here to here. The sound travels 2 times this distance because it travels from the person. Then before he hears the sound, that sound will hit the barrier and then it comes back. So it means that the sound travels 2 times the distance between the person, the source of sound, and the barrier. So using echo method, the speed is determined from 2 times the distance, because it will be the total distance traveled by the sound waves, then divided by the time, the total time taken by the what? The total time taken for the sound to be heard by the producer. That is it. So as you go there, please make a research about determination of sound by echo method. Then also determination of sound by echo method. Then after there, you talk about reverberation and also echo. What is the difference between reverberation and echo? Then how is reverberation minimized? And what are the disadvantages of reverberation as a form of reflected sound? So thank you so much, everyone. We shall not go further beyond this point. Yes, I can see some people are raising their hand. I can see some people are raising their hand, but anyway, maybe something else, but not about. Anyway, you can ask, but if it will take us beyond. I didn't want to go beyond 5 minutes, but if you have some questions, you can ask, please. But take note of the research work which I have left. That is determination of the speed of sound in air using echo method, reverberation of sound, disadvantage of reverberation, and how to minimize the reverberation of sound. Please, Kiza Apollo, you have something to ask? You have any question?
Yeah. Yes, Master. Yes. I was asked that I have not got the last assessment you have given us here of finding the speed of sound.
The assignment. You have not gotten what? Yes, Apollo. Apollo, please unmute. You've been not clear. You are not clear.
The estimate you have given us, the last one, the exercise.
The exercise.
I've not got it.
Okay, let me reshare it.
Yeah. Yeah.
So, Juliet, may you please unmute and ask something?
That was like some of us didn't check the screenshot.
Yes.
So can you please send the session activities in the group?
Okay, I will send.
Thank you, sir.
Okay, I will send. Or if not that, I'm going to share you with my numbers such that if you cannot access the group, you can access me on WhatsApp and then you get the exercise. So those are the questions. To those who can screenshot, please shoot it faster. Please shoot it faster. Then let me count 5 seconds. 1, 2, 3, 4, 5. Then let me just scroll downwards such that we get the last one very clear. Okay, that is it. So those ones who can screenshot it, please screenshot, and then we end this meeting. 1, 2, 3, 4, 5 seconds. Fair enough. So please, thank you so much. From the chat, I am putting my number, but let me just write them. Let me just write them. Okay. My number, WhatsApp number is, as seen from the screen, is 0751 963 763. 0751 963 763. That is my WhatsApp number. 0751 963 763. We only share academic content. Academic content. If away from academics, you should not go beyond. Yes, I will not tolerate content which is not academic. That is it. So thank you so much for attending to this session. Let me pray that we get other sessions such that we can expound more and more about these things. So, greetings to the family members there, greetings to the parents. Thank them for me. Tell them that we are really appreciating for enabling you to get this time with us. And I also take this opportunity to thank the HELP platform for putting in this program, because it is not a simple thing to join everyone in one classroom. They have enabled us to be interacting from everywhere we want. From everywhere, from anywhere you can even study. I can see even someone who is under the trees. You can wave to the people. You can wave to the people, you who is under the trees. So please, this has been today's session. Please allow me to stop here, and I will, let me just see. Allow me to stop from here. So thank you so much for attending. Good night.